Sure.
Let me give you one. This is
Oh, please, yeah.
website, and
Okay.
all the information is on there.
Great.
And I maintain this website, also maintain I gave you a card.
Yes, I have the card back there. Okay.
Yeah, so my personal website's on there.
Okay, great. Thank you. It's for me or to? Okay, great. Thank you. We're good? Okay, we're live. Okay, folks, we're going to pick up now with our final session for the weekend. So if you would please make your way to your seats. That's right. Well, you know, everyone's having a good time. It's all good. Okay, a couple of reminders. This is the last presentation for this afternoon. There will be probably a brief question-answer panel with all the speakers, so I hope you can stick around for that. And for folks who are watching online, if you do have questions you would like us to submit to the speakers, please do send those to the phone number, which is you should have access to through the conference email. And with that, okay, a couple more announcements. As I already mentioned, there were a couple of items of merchandise left in the men's room. They are at the registration table, so if you're missing some purchases, please go and claim those. Also, we have a few leftover boxes from lunch. So if, as you're leaving, first come, first served, you'd like to take a little extra lunch with you, please feel free to take advantage of those. They're in the fellowship hall in the back. With that, I will introduce one last time Dr. Marcus Ross. Marcus Ross is a paleontologist and has his PhD from the University of Rhode Island. He's a former professor at Liberty University in geology and is the president of Cornerstone Educational Supply. He has some resources, or had some resources out at the back table. I know many had a chance to take a look at those already. So would you please join me in welcoming back Dr. Marcus Ross.
All right. Well, thank you for sticking your way through the presentations, for absorbing a lot of information, a lot of data. My thanks especially to the other speakers for their great presentations. I have been enriched by them as well. So to bat cleanup then for our presentations here today and for our conference, I'm going to walk you through a version of some of the talks that I give. Oops, sorry. Can you hear on the microphone? No. Check, check.
I was using the desk microphone.
Yeah. All right. I can certainly do that. Yes.
Now muted.
Hello? Oh, all right. That worked. All right. Very good. Very good. So I'm going to walk you through some discussion and ideas about how we might understand the ways in which Noah's flood interacts with the evidence for plate tectonics. And the presentation here is based upon work within one of the textbooks that I've written along with several colleagues and co-authors. The textbook is called The Heavens and the Earth. We kind of figured that would be a good one for dealing with that. It's for introductory earth science classes in geology. My co-authors are Dr. John Whitmore at Cedarville University, Dr. Stephen Gollner, also at Cedarville University, and Dr. Danny Faulkner, currently with Answers in Genesis. And this is a textbook that is used at Liberty University, where I taught from 2006 to 2021. It's also used at the Masters University, at Cedarville, Patrick Henry College, and a few others out there. And so you'll get a bit of a sneak peek into what I normally do is about a 4-day lecture series for my classes, but we're narrowing our focus onto certain components of that. When we think about Noah's flood, thankfully, thanks to Answers in Genesis, we don't all just think about that box arc that we had growing up. That was a little perhaps too rigid in terms of this is the dimensions that God gave us, therefore it is a perfect rectangular shape. No, probably there's a little bit of seaworthiness to this craft rather than, say, barge look to it. But it is a barge, and it's designed in order to survive a world that is reduced to the same sort of condition it was at creation. That is, that it is reduced to a world that is unformed and unfilled with water absolutely everywhere. It's not a recreation. As Mark Twain is rumored to have said, history doesn't repeat itself, but it does rhyme. And so what we have in the Genesis account of the flood is an unraveling and an undoing, a cleansing of the creation through water to bring it to an uncreated state that it might be reworked. And we see in Genesis 8 how the world's rebirth from the flood mirrors in many ways its creation in Genesis 1. Now, we're going to hit a couple of biblical issues, but only a very few here as we focus more on the issues of geology and plate tectonics with the flood. But nonetheless, we have some clues and evidence from Scripture as to the reason why we think that the flood was global in extent. This is important for young earth creationists because, quite honestly, if we have this wrong and the Bible is not telling us about a global flood, then all of our models and methods for trying to discuss that are incorrect. So we want to make sure that we are on good, solid biblical footing for this. And I think that there's ample reason to think so. We have both Old Testament and New Testament authors that seem to be in concert here about the fact that all people, save Noah and his immediate family, right, the sons and their wives, were killed off during the flood. We're told in the Old Testament that there were only those 8. That is reiterated again in the New Testament by Peter, in 1 Peter, saying that 8 in all were saved through these waters. The flood is directly compared with Christ's return, which was mentioned in Bill's earlier talk, especially mentioning 2 Peter 3, and its judgment of all people. The flood is the historical justification for knowing that God has not operated the world in the same way all the time. It was interesting that that argument was being made for Christians who are interacting with Jewish folks who ought to know better. They ought to know better than the idea that all things had always continued. But the fact is that the historical reality of the flood is used as the justification for placing faith in the future whole world judgment of the coming of Christ. We also see that the flood's destruction was universal for humanity and global in scope in its description, particularly in Genesis 6 through 9. So what this means is, I believe, regarding geology, is that we have a bit of a choice to make. And this has been discussed and alluded to, but I'll put it in much more stark contrast here, that the geological record, including all of the fossils about which we've been discussing and thinking about, and as a paleontologist, I'm really happy to hear people talk about coal, even if you're talking about it as particles. I'm still thinking about it as plant particles. It is a record of either a recent creation and a flood, or it is a record of billions of years of life and its development and death and whatnot over Earth. To put it graphically, we can think of the flood in this way. On the left side of this is a young Earth creation conception of the geological column, and on the left is the conception that is shared by the vast majority of geologists out there. But nonetheless, the key here is that we are trying to explain the same exact data. And this is why we can't have both a universal global flood around the time of Noah and dinosaurs living and dying 150 million years ago or so, right? Because the flood rocks are either formed during the flood, as far as the dinosaurs dying then, or they died 150 million years ago. You can't end up having a global flood. But historically, that is kind of how we ended up getting into these sorts of arguments. Historically, in the 1800s, what we had were people. Oh, and let me bring up the little laser pointer here. There we go. In the late 17 and early 1800s, what we had were people who did believe that the flood accounted for much of the geological record, but then they started discovering lots of things and coming to grips with stuff that we take for granted. We take for granted that extinction has happened. But it's hard for us to put ourselves in the minds and the places of someone living in the 1700s for whom the concept of extinction is radically new. And it is because of the discovery of fossil forms that they started thinking, well, maybe there were other sorts of catastrophes during this time. And maybe Noah's flood was only limited to the upper amounts of geology in which we find people and civilizations and things like that. And eventually, of course, uniformitarianism won the day, and they got rid of the catastrophes here and viewed it as more continuous geological processes. The pendulum has begun to swing again as people have started to allow that catastrophes can happen in geology, but still only held within the context of an ancient Earth. Nonetheless, for young Earth creationists then, we think about those same exact rocks not in terms of things that happened hundreds of million years ago, but of things that occurred during a flood that occurred only thousands of years ago. Now, if that is the case, and we must explain some segment of the geological column with regard to the flood as the mechanism for creating it, we have a couple of questions that we need to answer. Questions that we need to answer before any of our models can even get on the table. These are the questions that allow you to further present your case. And my apologies, especially to any of the grammarians that might be in the audience or watching. I'm sorry, that should be from whence did the waters come? I'm a homeschool dad, so yes, we get this right, but I don't care. Where'd the water come from? And where did the water go? If your idea for how the flood operates answers only one of these questions, but not both, you don't get a chance to talk further. I'm sorry, that's just kind of where it goes. And this is why some other ideas about the flood that we've had historically with young Earth creationism quite honestly struggled. The idea of vapor canopy, which Dr. Humphreys mentioned as, passé, and for good reasons, passé, but one of the things that quite honestly that thing struggled with was, okay, we had lots of water that was supposed to have fallen down and formed the flood, but how did we get land again above the waters? Well, the mountains rose and the valleys sank according to the Psalms, yes, but how? And why is the water so big and thick and why is it not here anymore? So we've got to be able to answer these questions. What I would submit then is that the flood is essentially a geologic event. It is essentially a tectonic event. It is tectonic movements that are going to be able to answer the questions of from whence did the waters come and to where did they ultimately go. So to answer that, that means that we're going to have to learn a little bit about this stuff called tectonics. That's okay. I had the privilege for teaching students at Liberty University for 16 years. Most of my students were not science majors. Most of my students were scared to death of science, and they were even more scared to death of math. A simple rate equation of distance over time and beads of sweat would start appearing all over the audience. I'd say, how'd you get out of high school? And they said, barely. I snuck out the back door. It doesn't work here. But, so what we're going to do is get a run through of tectonics, and that will give us a platform for then understanding what's going on with the flood itself. So the lithosphere, this is a term that we have in geology. Litho means rock. Sphere means domain or realm in this case. So the realm of rock is a group of mobile units. This is what we refer to when we're talking about the plates of plate tectonics. They are made of lithosphere. And lithosphere is composed of a little bit of the upper part of the mantle of the Earth, and then all of the crust on top of that. So here's a schematic of the Earth. If we took the Earth and we cut it open and to look inside, we would all die. But if we could do that without dying, this was a common theme in my geology class. We learned a lot of ways that ye will surely die. Nonetheless, if we look at it, a good example of the Earth's interior is actually an apple. If you slice an apple and you look at how thin the skin of an apple is, that's roughly about the proportions of the thickness of the crust to the Earth itself. It's a really thin slice. And the mantle of the Earth makes up about 82% of the Earth's volume, so that's like the part of the apple that you're mostly munching on. And the core of the Earth, well, yeah, it's about the same size and proportion as the core of the apple. Now we got distances over here, and I would make my students learn to memorize these and draw this thing out for their exam. And I would tell them, there's about 10 or 12 components here. I hope you can memorize that. It's not that many, but it's more than you have fingers, so you'll have to work a little extra on it. But nonetheless, we've got our mantle and our crust and our core and down to our other components here. So if we zoom in on the side, what we have here is this is the lithosphere. We have some oceanic crust, and ocean crust is relatively thin and made up of the rock called basalt, which you all know very well because it's absolutely everywhere around here. Surprisingly on the continent, but that's because it oozed up on top of the continent, is sitting around. But the ocean crust itself is made up of basalt. The continental crust is primarily made up of granite and diorite, igneous rocks that have crystals big enough to see, relatively light colored. They tend to be black and white speckled rocks or some pinks and things like that. And the continental crust is thicker than the ocean crust. It is also more buoyant, and that was just mentioned by Bill Hoche. It tends to float on the mantle a little bit more because it's less dense. The ocean crust is about 15% more dense, and so it sits down a little bit lower, and the mantle rocks are more dense still. In fact, they continue to get more dense through the mantle, and then you get the outer and the inner core, which is made up of 90+%, 97+% iron, and it's trace amounts of nickel in it. That's really, really dense stuff. So the lithosphere is made up of a little bit of this mantle rock, and underneath that is another unit called the asthenosphere. That means weak zone, or the weak realm, and that's because the mantle rocks of the asthenosphere are quite plastic and easy to move around. They don't fracture and break because they're not hard rocks, whereas the lithosphere is the area where the rocks are hard enough that they do in fact break and crack when they're subjected to strain. Now, there are about 12 major plates on the surface of the Earth, and there are scores of smaller ones littered in between and amongst and around the main ones. On this illustration, you can see perhaps the North American plate, and you see how it includes both the oceanic material going all the way out to the middle of the Atlantic, so all this basaltic ocean crust, before you get to the North American continent itself. So our plate includes both the continental and the oceanic material, as does the African plate, the South American plate, the Eurasian plate. Some, like the Pacific plate, are made up almost entirely of just basaltic ocean crust. So there are certain features on Earth's surface that indicate that the continents have not always been in their present locations. These have been noticed going as far back as, pretty much the earliest maps that we have of the world. The very first person to make a notice that perhaps the continents were once joined together was a map maker, in fact, the father of the atlas. And he developed the original 5-color pattern for putting colors on maps so that there wouldn't always be two countries of the same colors. Ended up being a very interesting mathematical proof that was worked out only in the 20th century. But nonetheless, ever since the first maps of the New World started coming about, people started recognizing that Africa really looks like you should be able to just sort of nudge it back into place with South America. And North America looked like it just might fit there as well. And so this was referred to as the continental fit of argument. And I heard Bill talking just on the side here for a moment of Antonio Snyder Pellegrini. And he was an advocate for rapid and catastrophic movements of the plates prior to the plate tectonics revolution that occurred in the 1900s. He was talking about this way back around the time of Darwin. In fact, he published his book the year before Darwin's Origin of Species. But nobody read that book, nobody cared about it because uniformitarianism had sort of already taken the day, and he was advocating for some sort of catastrophic breakup of the continents. So this idea of the continents fitting together, everybody has kind of, if you ever spun the globe and said, God, are you going to make me a missionary here? Right? Some of you have played that game, right? You can just noticed this fit. Now, for every argument that I'll place up here, these are some of the classic arguments presented by Alfred Wegener, meteorologist and also with geophysical training, who presented this case in the 1920s and 1930s. He was ultimately, ignored. Not ignored, but believed to be soundly refuted, because for each of the evidences like these that were positioned, that he placed forward, there were evidence-based counter-arguments that were presented against him. For example, the continents look like they fit together, but if you actually put South America and Africa together, you find that South America is about 20% too small to fit in that little nook. So it looks good, but when you get close on the details, maybe not. Now, it turned out that there was an answer to that, but it was not available to Alfred Wegener at the time, and that was that the continental shelf extends for a long distance until it abruptly stops and goes down, and you get into the deep ocean. And once people started discovering where the actual boundaries of the continents were, that they weren't where the water is, but they're off deep in the water, now that 20% disappeared. And the fit between between South America and Africa was near 100%. But it would take time for that sort of thing to happen. But that was an argument. Wegener also made the argument that if you put the continents back together again into this thing that he called Pangaea, you would find that there were mountain belts that matched one another on what are now opposite sides of the Atlantic Ocean. That the rocks of the Appalachians, or I now live in Virginia, they call them the Appalachians out there, when in Rome. But my northern sensibilities come out on this. When the Appalachians are compared to, say, the Scottish Highlands, they have very similar structures, very similar types of rocks, and very similar sorts of fossils. The Atlas Mountains in Morocco have very similar fossils and rocks to the Appalachian Mountains. So matching mountain chains were proposed. But then again, there were counter-arguments of, yeah, but the northern Appalachians don't look like the southern Appalachians, which don't look like the central Appalachians. So Wegener, I think you're kind of cherry-picking what mountains you think look like each other. And there's a good argument there. Turns out that would have an answer as well, but nonetheless, Wegener said, yeah, but take a close look at the geology as well. We see the same sort of rocks on both sides, and we see similar types of fossils within them. We also see later on, after Wegener had passed away, that the locations of earthquakes and volcanoes around the world started to make sense in a world where there has been lateral movement of the crust. And it really would be the earthquake evidence that would start getting things going again, as well as evidence from geomagnetism. Looking at magnetic signatures in rocks would get people looking and saying, you know, Wegener might have been right after all. But why was Wegener considered wrong when he had such good arguments? And he really did. But again, there were some problems for him. One of them was his geological model of the collision of these continents to form Pangaea, create the Appalachian Mountains, could explain the Appalachian Mountains, but it couldn't explain the Rockies or the Cascades or the Sierra Nevadas, or 2/3 of North America's geology. So if you're a North American geologist and Wegener is saying, look, I can explain the geology, you're like, no, you can't. You just can't. His model could explain nothing about the Rocky Mountains. That's a big problem for North American geology. But there would be solutions that would come later, as science is an additive endeavor. So there's an example. There's the Scottish Highlands, right up over here, the Scandinavian Mountains, the Appalachians, and the Atlas Mountains. When you put them all together, they form a linear trend. And anytime you're doing science work and you find that your data plot out into a linear trend, you get excited. You might not know why, you might not have this clue as to what the real correlation happens to be, but there's some correlation going over here. Is there causation to go along with it? Wegener thought that it was collision, creating folded mountain belts, which is very much what we have around where I live in central Virginia. You get over the Blue Ridge into the Valley and Ridge province, and all the rocks just kind of are these giant waves that are eroded out. And so you've got that, the evidence of fossils. Wegener spent a lot of time focusing on the southern continents for his argument. It was one of the better developed ones, and it actually gives us an understanding that he never did read Snyder-Pellegrini's work on his views of the collision of the continents, because Snyder-Pellegrini actually had some very good arguments for the northern continents. He actually had very good arguments for why Europe and North America had to be collided and one, and Wegener never read that. Otherwise, he definitely would have included that information in his proposals. But nonetheless, looking at the southern hemisphere, we have several different types of fossils that are found on continents that are now separated by thousands of miles of ocean. For example, the mesosaur. Now, for my dissertation, I studied mosasaurs. Mosasaurs are big, huge marine reptiles that swam in every ocean that we have. Mesosaurs are little things, about 1 foot to 3 feet in length, depending on the species. They look like tiny, angry crocodiles, and they are not marine. They are semi-aquatic. They're the sort of critters that would be hanging around in streams and in lakes, but if you toss them out in the ocean and go go swim. Like, why? I'm not built for this. What's my name? Bait. It's, how you doing, chum? Right, that sort of thing. But instead what we find is that the same species of mesosaur is found on the southern tip of South America and in South Africa. There's about 4,000 miles worth of water between those two. It seems unlikely that the little mesosaurs could make it there. It seems very unlikely that this most unfortunate looking creature called Lystrosaurus could make it from Africa to Madagascar to India and down to Antarctica. It's an unfortunate creature. It really is. It's kind of the love child between a turtle and a pig. It's just a dumpy, small, herbivorous dinosaur that has no teeth save 2 tusks. So you're like, really? You're a herbivore with no teeth? How's that work? And you're like, well, you make do. But it's got this strange little face with this little sort of beak to it, a couple of long tusks, and a tubby sort of body, because you need a big stomach to toss all that vegetation and let the bacteria work on grinding it down for you. This thing is not a swimmer. It is not the Michael Phelps of the fossil realm, and yet it's found in Antarctica and India and Africa and Madagascar. And then you have Glossopteris, least likely of all of them because it's a plant, so it's not really going anywhere. And yet its pollen and its fossils are found across all 5 of the southern continents. Now, again, there were counter-arguments to why this might be the case. There are arguments, maybe there were land bridges, or maybe the pollen is being distributed by wind, in strong gales and whatnot. Once the pattern for earthquakes started showing up, however, it started to become very clear that there's something strange going on in the world. This is a map that shows all of the earthquakes of magnitude 4 or greater in the world during the entire 20th century. And what we can see is this is not a random distribution at all. There are clear places where there is lots and lots of volcanic activity, and there are other places where there's really nothing at all. We happen to be in an area where there's a moderate amount of activity, and if you're up in northern Canada, there's nothing going on. Well, there's nothing ever going on in northern Canada, but geologically speaking, there's nothing happening in northern Canada. There's nothing happening over in Virginia. We had a good little shake back in 2011. We had a magnitude 6 earthquake that struck in Louisa County about an hour and a half from my house. But that was the biggest earthquake that we had in 100 years. In the same place, Louisa County popped off. It's a little old fault that every once in a while lets off some strain that is built up in North America and just kind of goes, okay, that's better. It was a small chiropractic event. But nonetheless, we have a lot of earthquakes in Southeast Asia, over towards Middle Earth, over to New Zealand, along the western side of North and South America, right? We call this the what? That's right, the Ring of Fire. And we call it that because not only do the earthquakes show up over here, but this is where all those volcanoes are. All those big stratocone volcanoes, the Mount St. Helens types, the Mount Fujis, the Mount Hoods, all that sort of stuff. Mount Doom, from Lord of the Rings, the picture that they have in the movies is an actual real volcano in New Zealand. So you can visit, that's on the northern island. But it's called that because of all the volcanic activity, and it coincides with the earthquakes, but also there's a lot of earthquakes where there aren't volcanoes, but there's a pattern here that needs to be explained. It would turn out also during the 20th century that there would be a number of discoveries in the ocean basins that would lead us to understand that the ocean basins themselves have moved. One of the other reasons why Wegener never got his idea fully off the ground, especially with North American and many European geologists, is that he didn't have a mechanism by which he could explain the continents moving. He viewed the continents kind of like glaciers, grinding their way over the oceans and plowing their way through. And a quick back-of-the-envelope calculation shows whatever force would be capable of plowing a continent through the ocean crust would probably peel the skin off of the Earth. It's just not going to work. And he suggested perhaps tidal forces from the moon, but he knew that couldn't work, and everybody else knew it too. He just didn't have a mechanism. And what he was missing were some data that would be coming out after World War II that would help to solidify the idea that the ocean crust itself is moving and provide a means to reduce the amount of force necessary to get those continents moving around to levels that would be understandable and likely, and as we turned out to be true. So a couple of things that we notice. One is that there are extremely large, long volcanic mountain chains that we never see because they're still thousands of feet underwater. We refer to these as the ocean ridges. In the Atlantic, we call it the Mid-Atlantic Ridge because it's located pretty much down the middle of the Atlantic. But the ocean ridge close to here is actually quite close to here. The Juan de Fuca plate is a small plate subducting under Washington in Oregon. And you only have to go a few hundred miles offshore before you get to the point where you get to that mountain belt. And it turns out that that mountain belt is where volcanic lavas are coming up, and two plates are moving in opposite directions. So this isn't just a mountain, it's actually a crack that is elevated because there's a lot of magma buoying up the area. And so it's lifted up this way, but it's not solid across. There's cracks in there and they're moving apart. The discovery of magnetic reversals was key to getting people to start thinking about Alfred Wegener's idea. First, they were discovered in rock units on land, and finding that when they looked at the magnetic signature of minerals inside the rocks, they would point to the north, and then a couple of layers down, they were pointing to the south, and then they were pointing to the north again, they were pointing to the south. This is really, really weird, what's going on? Or they would find that there seemed to be shifts in where they were pointing to north in particular, and on different places, on different continents, you couldn't quite match up where north was. And North American geologists thought the Europeans were doing this all wrong, and the Europeans thought the North Americans were doing this all wrong. And it turned out that, well, if we actually start moving the plates around, we can keep aligning north back through time. That was discovered also then on the ocean floor, this kind of striping pattern in a sense. You can't see it with your eyes because the rock looks the same, but when we tow magnetometers over, we start getting peaks and troughs of how strong the magnetic field signature is, and it turns out that those are identical peaks and troughs going away from the ridge in the center. You go, huh, something is happening here. So if we drained all the water out of the ocean and took a look at it, we would all surely die, right? So second way that we can do this today, take all the water out of the ocean, and these light-colored areas indicate these are the places where we've got these oceanic ridges. And it's kind of like the seam of a baseball. You can kind of trace it with your finger all the way around, and every once in a while it will duck under a continent. So if we're looking at the Pacific ridge over here, it comes up, and then it disappears right around the Baja Peninsula where it goes underneath the continent, and turns over here into a transform fault. So our San Andreas fault has actually got part of California being dragged along with the Pacific plate to the north and west. So when the big one hits, California is not falling into the ocean. It's just drifting closer and closer to you all, and I know that you're already worried about how many Californians are here, and it is. So, but it pops out again around Berkeley and around San Francisco, and stops being a transform fault and becomes another ocean ridge right over here. And so you can trace this thing as it kind of goes all over the place. And what this tells us, if the continents have been moving, and if the ocean has been moving, then it tells us that the created world was quite different. And you look at this as a reconstruction of, a potential reconstruction of the world done by Answers in Genesis. Where's North America? I mean, okay, I'm a geologist, I might know where it's supposed to be here, but nonetheless, you look at that and say, North America isn't where I think it is. It isn't. At the beginning of the flood, it's very likely that the entire North American continent was rotated 90 degrees clockwise, and Virginia was sitting in the southern tropics. So interesting, very, very interesting. So if the created world was different, we have a few things that we think about from Scripture, and we don't have this written out plainly for us. We can't say for certain that we don't have volcanoes, that we don't have big earthquakes. But what we do have for a description of the world at the end of creation is one of what seems to be peaceful, harmonious existence. We're told that animals are to be eating plants, so we don't seem to have any sort of view of carnivory out there. The world is very good. It would seem that when God created a world in which humans and animals and plants are supposed to thrive, that large earthquakes and volcanoes that tend to kill everything would not be part of that creation's economy. So we think probably that we would not have some of the sorts of features and structures that we have today that are associated with these plate movements. We wouldn't expect to have large amounts of plate movements and ocean ridges, no massive mountain chains like the Himalayas or the Cascades over here, because we believe that these are actually products of the events that made the flood, and the flood changed the geography of the world. Little to no earthquakes or volcanoes. There might be some, I'm not positive, so I'm not going to be dogmatic about that. But when we think about the original creation, I don't think that it has quite the same features that we see in the modern world. But how do we explain this? The conventional geologists eventually came around to the idea of plate tectonics. They took Wegener's continental drift and they wedded it with seafloor spreading, a concept that was written. A beautiful paper. You don't get scientific papers that have really nice titles. Mostly it's some sort of boring gobbledygook. But this one was titled An Essay in Geopoetry. You say, I almost might want to read that. Then you start reading it and you're like, I don't know that I really want to read it, but I do. And so the conventional side of things has a storyline. It has a series of explanations. It has an account. For young Earth creationists, one of the things that plagued us for some time is that we spent a lot of time being not evolutionists, but we spent less time being creationists. It is one thing to be against something, but it's another thing to be for something. And I'm privileged to be in the group that is speaking here today because many of them have been involved with projects that were advancing creationism for creationism. And we need to be able to do that because the only way that people will change their perspective from something like an evolutionary or an old age worldview is to be presented with a story that is more compelling than the one they already think. And that means that we've got to take the data that exist and explain them in a way that is satisfactory. And that leads us to catastrophic plate tectonics, which was first proposed by Austin et al., and we're privileged to have one of the authors of that paper, Russ Humphreys, with us today. He was there in 1994 when this was presented. The Gang of Six, I heard you were called back then. Way to go. By other creationists, I might add, who didn't like the idea of plate tectonics. Henry Morris, for the very good work that he did, was always quite skeptical of plate tectonics. In fact, not quite skeptical, highly skeptical, antagonistic towards plate tectonics. But nonetheless, eventually, now we see that all the major creation ministries recognize catastrophic plate tectonics as the best model for explaining the mechanism behind the flood. Is it the correct model? I don't know, but I think that something that either it or something like it is very much going to be true, right? We always have to reassess our models and try to refine them and whatnot. But this idea was proposed in 1994. It envisions a rapid continental sprint rather than a continental drift that occurs during the flood. And according to the work of Dr. John Baumgardner in particular, and I'll show you some of his work in a little bit, the modeling for this was that the flood begins with the onset of what is called subduction. Subduction is when oceanic crust, which I mentioned before is more dense than the continents, is pushed up against the continents, and when you have something that is dense and something that is light, and you push them together, the dense one is the one that goes down. You can do this, as Steve Austin would say, bathtub experiments, right? You can do this in a bathtub. Yeah, the number of times he's talked about learning something in a bathtub makes me a little uncomfortable. But nonetheless, if you took a plank of maple and a plank of pine, and you floated them in the bathtub and you pushed them together, the pine would eventually push on top of that maple because it is a lighter wood. They're both going to float, but when push comes to shove, literally on this one, when push comes to shove, it is the maple that has to go down because of its density. Likewise, what we see is that oceanic crust, when it meets continental crust, is forced underneath because, again, the continental crust is about 15-20% less dense. It's going to float up higher than that. But pushing that ocean crust down underneath the continental crust, or under another piece of ocean crust that is lighter and more buoyant, has consequences. All actions have consequences. It was a key theme of my classes when I would talk to my students, especially about our interaction with the creation. And if we're thinking about stewarding our creation well, all actions have consequences. Also, the actions of inactions have consequences. So the flood begins with subduction, with ocean crust that goes down underneath some of the continents. The pre-flood ocean crust begins to sink into the mantle near its border with the continents. And Baumgartner's mathematical modeling showed something very fascinating, that at certain strains and certain temperature pressure situations, the rock that makes up the mantle switches between being resistant to things moving through it to allowing things to move through it very, very quickly. And once that switch was made, the ocean crust is able to dive down through the mantle at rates of kilometers per day. Right now, the movement of subduction is only happening at centimeters per year. It's very, very slow. But the physical properties of the mineral olivine, which makes up the vast majority of especially our upper mantle, allow for rapid shear to occur under certain conditions. And this would allow a runaway capacity to this subduction. This would allow the subduction to start moving, and then start moving faster, and then go faster and faster and faster and faster, a positive feedback reaction. Now, as that ocean crust sank down towards the interior of the mantle, diving its way towards the core, that would cause it to fracture and break and move apart, because the upper part is still rock, it's still brittle. You start pulling rock in two directions, it will break. And it breaks in a big way, and, well, the mantle underneath it immediately melts and rises to the surface. It happens in this, for the same reason why pressure cookers work. How many of you have a pressure cooker that you use at home? The good old Instant Pot that is out there now. It's one of my favorite kitchen items. Good gracious, this thing is awesome. You can do everything. You can stir fry things, and you can make yogurt. I mean, it's quite versatile. But how many of you remember the old pressure cookers? The big old knobs and the bomb in your kitchen. That's right, yeah. And at my house, an emergency eject button to toss it out of the kitchen just in case. No, but a pressure cooker is a great analog to what goes on with the ocean crust and the mantle below. See, the mantle is very, very, very hot because rock is a great insulator. And so this heat is trapped underneath the ocean crust. And the temperature is high enough that this rock will melt. But it can't, because it's got so much rock above it that it is held in a pressure state that maintains it as a solid. The pressure cooker allows water to boil at higher than normal temperatures because you keep lots of pressure on top of it. So you can get that water to be 230, 240 degrees Fahrenheit before it starts boiling inside here, and things cook a lot faster that way. So the mantle would like to be liquid, but it can't be because it's got too much stuff on top of it. Well, when you break that rock and you rip it apart to the sides, all of a sudden the pressure is gone, and immediately it changes phases between solid into liquid. And the particular liquid that it makes turns into basalt. Even though the mantle below is actually a different rock and it makes up something called peridotite, the stuff that melts is the stuff that will make basalt, and there will be some minerals that are still going to be fine and comfortable being solid at that temperature, and they stay behind. So as the crust sinks, new magma rises, and that starts creating these ocean ridges. The sinking of the old crust creates a runaway feedback. As I said, Baumgartner's modeling of this shows that as it goes down, it's able to move faster and faster and faster. Kind of like if I took this microphone and I got too close to one of the speakers, we would get that rapid feedback that would cause a big problem. The only way to stop that is to step away and cause an opposite positive feedback. The opposite positive feedback is things got quieter, which means it didn't get picked up as much, which means it got quieter again, and so on and so forth. We have positive and negative feedbacks. A positive feedback extends the original shift and continues it. A negative feedback tries to balance it out with something else. So in my college classes, my students were always talking about they wanted positive feedback. I said, yes, but negative feedback is actually really important in nature, and it's not a bad thing. We just tend to associate it in different ways. So schematically, in a simplified fashion, it would have looked something like this, slicing our way through the earth to look at what's going on. We have subduction happening down over here. That subduction is causing the mantle to convect, and in the areas where the two convection cells come back up and where the crack and the rift has happened, we have the flash phase change between solid into liquid. That material would come up, it would impact the bottom of the ocean water, which would immediately vaporize large amounts of the ocean water, causing it to go in these huge geysers. If you've ever been to the Creation Museum, there's a phenomenal animation of the initial rise of the water out of these geysers, if you will. It's very, very stunning. It's nicely done. So there are two sources of water that are talked about in the Genesis account of the flood. The fountains of the great deep and the windows of heaven. The Bible, both of these, I believe, are components that are caused ultimately by the ocean ridges themselves, made during the flood. The fountains of the great deep, Dr. Humphreys mentioned yesterday, the Hebrew word for this is techom, and techom is, as he mentioned, it's a big body of water. And we can think of this as the oceans. The fountains of the great deep are the oceans. Now, we have a tendency to think of fountains as big, huge, spurting things because we live in the 21st century, quite honestly. And we've built fountains. But if you go into the Old Testament and you look at other places where the word fountain is used, fountains are little springs that dribble water out from a rock. They're not these big geyser-like sorts of things. They can be. That can be a fountain. But that come thou fount of every blessing, it's really a pouring out. And so I think that when we hear the fountains of the great deep burst forth, what we have is actually the movement laterally towards the continents of the oceans themselves. They are driving themselves over the land. The windows of heaven here is a Hebrew euphemism for rain. You see this also later on in the Old Testament after the defeat of the prophets of Baal. The prophet looks out and he says, "Behold, I see a small cloud," or he tells the king says, "I see a small cloud. It's like the size of a man's fist." And then it begins to rain. They said, and the windows of heaven were opened. So I don't want to look at this and say that this is some sort of technical term. Again, like I mentioned yesterday with the Hebrew word min and le min hu, the convection. These are terms of colloquial use. But nonetheless, the windows of heaven were opened. There was a whole lot of rain. And in fact, the word that is used for rain here in the flood narrative is geshem, which is different from another Hebrew word that is used more commonly for rain. Geshem is probably more associated with seasonal rains and downpours. And so I think it's important actually that the first time that we see the word rain used after Genesis 2, which is the standard Hebrew word for rain, geshem is the one that shows up here. This is an important rain. This is a special rain. This is different. This is a heavy rain. So I think we actually had plenty of rain before the flood as well. It's not the same thing, but in English we translate them as the same word. That gets us tripped up from time to time. Now, during catastrophic plate tectonics, the water from the oceans is moved over the continents in 4 different ways, 2 of which are important and 2 of which are kind of ancillary to the whole thing. The geysers at the mid-ocean ridges are vaporizing wash of water, which condenses and forms massive amounts of rain. So I think a lot of the initial rain and the rain that continues on during the flood is actually coming from this kind of source. Yes, there are rain clouds that are raining, but there is also all of this water that has been lofted high into the atmosphere and is coming back down all over the place, even in places where you probably aren't seeing any clouds. There's just downpours coming. The subduction of the ocean crust is not something that is smooth. In geology, we often talk about plates sliding past one another. That's nice. That sounds great, but really what they are doing is they're grinding against one another. Take two pieces of sandpaper and rub them slowly and hard against one another, and you get a lot of friction out of that. If you take the ocean crust basalts and you have the continental granites and you're trying to slide one underneath the other, there's going to be a lot of friction. And when that friction happens, because the ocean crust is going down, it's going to pull the continents with it, especially at the margins. It's not going to drag the continents underneath the mantle or anything, but it's going to pull down. And for every foot a continent goes down, that's a foot more of ocean water that goes up over top of it. The most important one here is actually the third, and that is that the new ocean crust is warmer and it's lighter than the old ocean crust. So as the old ocean crust is being subducted down into the mantle, the new magma that's creating new ocean crust is thicker because it's lighter and more buoyant. It hasn't contracted under cooling situations yet. And so it is actually lifting the bottom of the bathtub, if you will, up. And so every foot of elevation that it raises the ocean level itself another foot. And we're not talking about just a few feet. We're talking about at least 1 kilometer's difference in elevation between the old ocean crust and the new stuff. That's a lot. Now we're talking 3,000 feet worth of water rise. And this is why the flood really happens the way that it does. At least this is what I think is the scientific backdrop for what's going on as God judges the world, is that the oceans are rising, and that is pushing the physical boundaries of the ocean up over all the continents. The least important of these, but still something that is happening, is that ocean water, like everything else, expands when it gets warmer and contracts when it gets cooler, and the amount of heat that is being generated here, some of that is getting put into the oceans, and the oceans are probably rising a good 40 or 50 feet or so, just on the basis of thermal expansion, in addition to everything else. But we're getting thousands of feet from the new ocean crust. We're probably getting hundreds to thousands of feet of depression where we've got the frictional downpull, and then these other things are causing erosion and whatnot. So that's what we've got here. We've got a lot of different things going on. And in the midst of this, not only is there subduction, but the continents are now moving around. They are shifting their position and being dragged by these large-scale convective systems within the mantle. Baumgartner put this together in both a 2-dimensional and 3-dimensional computational simulations. He's a geophysicist who specialized in creating computer programs that could analyze tectonic movements. His program, called Terra, was for some time perhaps the most widely used and most respected tectonics modeling system in the world. He built it flexible enough that any old Earth advocate could put in the parameters that they wanted and see how tectonics worked, but he also built it flexible enough that as a young Earth creationist, he could import parameters that he thought might be more realistic about things. But what we might not be able to see, so I'll kind of point it out here. Here is North America. Okay. There is Africa. There, South America, Antarctica, India, and then you have Europe and Asia kind of coming off towards the back here. So this would be a Pangaea construction, all land, and he started with this, which we don't believe is actually the beginning of the flood. But he wanted to see, can you model the movements of Pangaea and get from Pangaea to our modern plate positions? How long would that take under these types of situations? And he found that you could very easily get Pangaea broken and split apart in the continents to where they are today in about 150 days, which is half the duration of the flood. And so the continents are actually in a different position to begin with. They mash together to form Pangaea because we have to explain things like folded mountain belts, like the Appalachians. How do you get those? Well, the rocks have got to form flat first, and only later on can those flat rocks be bent and folded into wrinkles, if you will. So there we have a little bit later on, the continents start to split. You start to see the Atlantic Ridge form over here, and they continue on, throughout that. And he has a whole series of animations Again, both in this kind of three-dimensional view of the world as well as two-dimensional, kind of what's going on in the mantle with all of this. But how does this all stop? After all, a positive feedback mechanism is a dangerous thing, right? If I just kept standing closer and closer to the speaker with my microphone, it would be really bad and you would eventually all leave. Understandable, I could let you go for that one. Well, it turns out, remember, of course, at day 150, God remembered Noah. This is actually the most important phrase in the entire flood narrative. It is the single point upon which the entire flood narrative hinges, and it's kind of mirrored on both sides by this one verse. In Hebrew, that's referred to as a chiasm, where you build a story and then you match it on the other side, and there's a central point, usually, upon which you're supposed to focus your interest, and that is God remembered Noah. As the pre-flood ocean crust is eventually replaced by this warmer ocean crust, it is more resistant to being subducted. The reason why the old ocean crust from the pre-flood world could be subducted is that it is cold and it is dense, and in some places actually more dense than the mantle that's directly above it. But the new stuff that has come up is not dense. It's light and it's buoyant and wants to stay up, and so when it starts hitting the margins, this system starts to slow down. And when it starts to slow down, so do all of the other related processes I've been talking about. So the cooling of the ocean waters, cooling of the ocean water and the new ocean crust, as that new ocean crust cools, it contracts and it shrinks down to size, and for every foot that it goes down, the waters recede off of the earth. And it takes some time for this to happen, months, right? Noah lodges up against the mountain of Ararat at a certain time during the flood. If we put it on our own calendar, it would be around July. And it's not until August that he actually sees the tops of the mountains, and it's not until February that he actually gets out of the boat. As he gets in, actually, it's a year and about 10 days between when he gets on board the ark and the flood starts to when he eventually leaves the ark with the animals. A year and 10 days. So I believe that catastrophic plate tectonics is actually able to answer those two questions that I started the presentation with. Where did the waters come from? Well, they came from the oceans. We don't need some sort of exotic extraterrestrial source of water to explain how the flood occurred and why we have water that covered the whole world. It was the waters of the oceans. And where did it go? Well, we still have it. It is the water that is in the oceans today. It was displaced, it was lifted, wafted over top of us, but eventually it went right back down. This matches very nicely with the description of the flood, because God said in Genesis 6, when he kind of announces his determination to destroy the world, he said, I will destroy the earth with the earth. It's a fascinating verse in Genesis 6. I will destroy the earth with the earth. Not with something else, not with things external, not from the power of heaven coming down and doing something outside. I'll destroy the earth with the earth, and all flesh will be consumed in this. But Noah found grace in the eyes of God. There have been some predictions that were made based in CPT, and some other things that were discovered that are very consistent with catastrophic plate tectonics. One was the extremely rapid magnetic reversals, another project actually that Dr. Humphreys has worked on in the past, and also the existence of very cold material that is still down in the depths of the mantle. And in the interest of time, I'm going to skip directly to that one here. We're almost done. This is a wireframe image of the Earth's interior, taken by a really fascinating process that has only really been developed over the past 20 plus years, and that is taking seismic data, not just to determine where an earthquake is, but by mapping out seismic data from all around the world and then running it through a program, picking up even tiny little earthquakes, and then running them together. You can actually start to get good pictures of what's going on deep in the interior of the Earth. And what we've got here is the wire on the outside is the Earth's surface, and then there's kind of a ball in the center. That is the Earth's core. So that's the liquid iron outer core. And then there's these other blobs. Now, the darker of the blobs, such as this one, is a dense and presumably cold material that is hugging the Earth's core. It's not in the Earth's core because it's not that dense. The Earth's core is extraordinarily dense. If I had a 1 gallon jug of milk, right? Quick guess over here from the audience. How much does a gallon of milk weigh?
A gallon?
Its volume is a gallon, but what is its weight?
8 pounds, roughly.
Outstanding, 8 pounds, just a little over 8 pounds. There's an old term in the cooking world that says, a pint's a pound the world around. 1 pint of water, 1 pint of oil, yeah, there's slightly different, but basically a pint's a pound. 8 pints in a gallon weighs 8 pounds. Next time you're coming from the grocery, you just do a couple of lifts, and then, it's like getting your extra steps, do a couple of those. A gallon of granite weighs, not quite 3 times that. So while water has a density of 1 gram per every milliliter, granite has a density of about 2.7 grams. So that 8-pound gallon of milk turns into a 30-pound-ish gallon of granite. It's about 34 pounds or so for basalt. But if you took a sample of the inner core of solid iron nickel, that's a 100-pound gallon. So even the mantle, which is pretty heavy, gets to be 50 some odd pounds for that gallon, isn't anywhere near the density of the iron. So these plates have gone down and they basically ricochet. They can't get there and they bounce off. But what's really weird is that they're there. These are slabs of cold, dense material that is down deep near the hottest parts of the Earth. The Earth's interior, the center of Earth's core, is thought to be about as hot as the surface of the sun. It's that hot. And rock is that good of an insulator, which is why we're okay up here. But if plates have been moving slowly and gradually over the course of hundreds of millions of years, they would have had plenty of time to establish equilibrium with their environment. Crustal plates, especially ocean crust, is relatively thin. It's only about 4 miles thick. And the Earth's mantle is almost 2,000 miles thick. So you're dealing with just a couple of pieces of paper going into the dictionary here. And yet it's still there. This makes sense if those plates have gotten down there recently and haven't had time to establish thermal equilibrium. Schematically, we look at it like this, and it's been referred to in this conventional literature of this being like plate graveyards. Now, just a few years ago, some other scientists have said, we think that this is actually made up of entirely different material. Maybe it's not cold, dense ocean crust. Maybe it's just super dense, hot material of some other type of structure, but we don't know what that is. Well, that's possible. It's a hypothesis, but if I say this and somebody says, well, we've already shown that this is other material. No, you haven't. You've just come up with an alternate explanation. 2 different hypotheses. There needs to be more tests on that, but for the moment, we do know that plates can go through the mantle, and we know that there's material down there that gives us a signature that looks like recently broken and dropped down ocean crust plates. So what this tells us is that our world, the judged world, is different. If the pre-flood world was different, the world that we live in is quite different. So because of the flood, the continents are in different positions, and Pangaea was actually only a mid-flood configuration, or I think actually fairly early in the flood. And because of the flood, new mountain ranges like the Himalayas, the Rockies, the Cascades, now exist. So what was then versus what is now are really, really different things. And thinking about that difference, because of the flood, geological disasters now are somewhat common. Thankfully not so common that we have to be worried all the time about them, but common enough that we hear about them. We're constantly reminded of the judgment of God, if we have the ears to hear and if we have the eyes to see what God is telling us. We have these echoes, these reminders of the judgment with us every day. I mean, this was a devastating earthquake in central China in 2011. And I'm not pinning this earthquake on any particular sin of the people there. It doesn't have to be because they sinned, right? God does say sometimes because you sinned, this is going to happen. But he didn't say that in 2011 to the people of China. We live in a broken world. And fortunately, we have a God who has walked among us and knows our grief and knows our pain and knows our sorrow and knows how to heal it. I had just finished a section in my class on tsunamis and earthquakes when the Japanese tsunami of 2011 struck. And how many of you enjoyed disaster movies? Like watching movies like, there's a few guilty hands going, maybe. I used to like watching disaster movies. They're fun. Most of the time they're quite stupid. They make no scientific sense whatsoever. The Core is perhaps one of the worst scientific movies of all time. I knew geologists who would assign that as an extra credit activity to their students. And they actually had to put a cap on how many points they gave for every scientific error that was in the movie. They're like, you can get up to 25 points, no more than that, because there's plenty more than that in the movie. But I just finished talking about tsunamis and earthquakes, and this occurred. It was a Thursday. I had one more day of class when this occurred, and then then I went to spring break, and I spent most of spring break watching the news and watching this happen. But also something I did during that spring break is I watched the movie 2012, which came out in 2011. But nonetheless, it was an not to mention that the movie, while technically well done, also didn't have like a great hero person. He was there to save his family, but he really didn't care if he had to step on a few people along the way. Wasn't really heroic. He was just, trying to save his kid. Minor hero. But when I saw this, it really kind of changed my perspective, because I could see the catastrophic processes on a small scale, like Mount St. Helens, like the Missoula flood, that were happening, and seeing the devastation and what was going on, and going, okay, I have a small glimpse now into what was happening when God looked upon the world and said, it has gone so far bad that I am going to wipe it entirely clean. I have to cleanse it. But we do have the promise that that cleansing of the world, that judgment, was finished. We are fortunate that all we have are echoes of that, and that God in his great mercy said that I will never again destroy the earth with a flood, a mabul. That is the Hebrew word that is associated with this event, and is only ever associated with this event in the entire Old Testament. In the New Testament and in the Greek Septuagint, the word there used is cataclysmos, and likewise it is reserved only for the flood event. God has promised never to do one of those again. And it's another good indicator that we're not talking about some regional or localized flood, because if that's the case, then God's done that all the time. There's never been a point of reprieve. But also notice what God has promised, that he will never again do this, not just to people, but to animals. Never again will all life be cut off by the waters of a mabul. And for the animals that live in the far-flung places of the world, this promise is theirs too, because what we have dominion over is why the blessing goes everywhere. We are the ones who steward and have dominion over this world. We were given this promise, and to everything under our charge is that promise as well. And we can take joy in knowing that God is going to continue his mercy until the end, when his last judgment comes. And that is a judgment we need not fear, because it is the coming of our King. And that will be a glorious day. With that, thank you very much. And if you have any questions, we're coming up on a Q&A time. Looking forward to that. And last again, if you're interested in finding some good science supplies for your homeschool co-op, for your kids who are doing homeschooling or have a Christian school and are a teacher there, we would love to be able to help you out with those science materials. So thank you all very much. I'll turn it back over to Zach.
This button there.
Oh,
You're good. Oh, did you already hit it?
yeah, I had put it on.
Oh, in that case, I may have did it the wrong way.
There we go. Should be coming right back
Ahead
to
of
you.
me. Thanks. Okay, at this time we'll have a short break, maybe 5 minutes or so, while we get things set up for our speaker panel. So 5 minutes to get up, stretch your legs, But don't go too far away. We'll be getting started in just a few minutes here. Thank you. The plan was to move this whole. I'll wait for Dave to get here because he'll know exactly what to do. Go sit down there, okay? I'm gonna get things set up. You can walk around, yes, you can walk around. Okay, so how are we doing this?
It's very strange. That can stay there, but this has to move over to there.
Okay, great.
So you're gonna grab that.
Yep. Are we not plugged into anything that's gonna
We are.
hang up? Okay.
We'll see how
Whoop,
far
there
we
you go.
can get.
Right, right. This big cable here is power.
So we can move that one.
Oh, well, it's got plenty of slacks just tied up.
And the cable's coming right about now.
Fully charged. Oh,
Let's see how far we can get this time.
yep. There we go. Wrong. Oh, hold on something. What do we got now? Keep going?
Nope.
Oh, nope.
I think we went too far.
Okay.
Against that one? Bring your cable back.
Let's see. Should we do this?
We're trying to center this if we can.
Yeah. Okay.
And then this whole pulpit has to go back over.
Oh, okay. I see what you're saying.
Well, nope.
Okay.
Tablecloth first.
Oh.
I had it, just had to wait.
Gotcha. Thank you again for your flexibility here. Are these the mics we're using? These the mics we're using?
They are, and mic stands.
Could we put this down, you think? Would that work?
The pulpit?
Yeah.
We can, but that's where Hannah's gonna stand.
Well, it won't be Hannah, it'll be me, actually.
We can. You wanna use, you put your laptop on there if
I
you
think
want
it'd
to.
be easier for me if I was off to the side, kind of looking at the
Okay.
whole panel.
We can put it down.
Otherwise, we're splitting the speakers. Let's see if that works.
I can unplug it too.
Okay.
You just unplug the whole thing.
Oh, wow. So maybe what I'll do is I'll sit off the side here. I'll just share a mic with whoever's sitting here. So I can use that. It works. Oh. Shall I use it? So let's do that, yeah. Yep, I agree. You're here first, so you can pick your seat. Yes, I do. For that. Turn on. There it goes. Yeah, yeah, it's fine. Try to make sure they're all turned on.
What was the matter with the
Lapel mic? We're not sure.
the portable mic?
Yeah, we're just avoiding it for now until we can debug it. folks here in the audience. So I'm going to start off with Dr. Humphreys. First question is for you. So in your cosmology, which you presented on last night, the Toward a More Biblical Cosmology, the question is, would you expect galaxies to appear younger with distance? And this question is specifically with regard to the James Webb Space Telescope. There's been a lot said about how the most distant galaxies appear very mature. Would that not be what you would expect in your cosmology, or how would you explain what we're seeing in deep space?
No, I wouldn't expect them, and I didn't expect them to look younger. That's what the Big Bang Theory would think. But my cosmology would have them looking pretty much the same everywhere. When that light started out to us, they would all have about the same kind of distance. So,
Okay,
that's
so
what the James Webb saw, by the way. I wish I had predicted that in print.
the JWST sees that the most distant galaxies look mature.
Yes.
Correct? So in your cosmology, that would be reflective of the fact that they really have been around in their local time for billions of years.
Yes, that's right.
Okay, so that's not actually, you're not looking back in time then, the way that a Big Bang theorist would say we're looking back in time towards the Big Bang. That's why they expect to see younger galaxies.
Well, we're not looking back in much time.
Yeah. That's interesting. Okay, so thank you for that. Let's see. We'll do one now for Dr. Marcus Ross. And this is with regard to your presentation yesterday on creating kinds. And this is, I think, a somewhat hot topic. So when detecting created kinds through baraminology and these sort of analyses, and we have these phylogenetic trees you showed us, spreadsheet of data that evolutionists would use to create family trees of different species and so forth. And then creationists now are using that data and analyzing it differently. So when we do that, and I'm inflating the question here a little bit to give context, are we at risk of introducing evolutionary bias into our analysis?
Sure, that's a very good question. Thanks to the folks online asking me. I would say no, I'm not introducing evolutionary bias, at least in any level that's going to cause concern for that. In the same way that I don't think that we're introducing odor bias when we look for, say, the magnetic pattern on the ocean floor that led to our discussion for tectonics. To give it, to think about the organisms that we do these data sets for when we evaluate the skeleton. Let's say that the skeleton is actually this microphone right over here. Whether I'm an evolutionist or whether I'm a creationist or whether I'm something entirely different, the features of this structure are the same. Now, we might not always exactly see it the same way. There might be a slight difference that we would code for the color of the mic. You know, I've got a little yellow thing here. I'm going to say that big bird yellow, and somebody else is going to say that's lemon yellow, right? But the reality is that we're at least both agreeing that it's yellow. And so when we're looking at a skull, for example, we can see that there's funny little bumps or horns or there's knobs or there's a connection between two bones in the skull. We should be able to agree that this bone and this bone are in contact with one another, and the contact looks like a V or it looks like a straight line or something like that. People can make mistakes. We are all humans. And that's, an evolutionist can make a mistake in describing a fossil, a creationist can make a mistake in describing a fossil. But on the whole, this is one of the reasons for publishing the data set and publishing the descriptions so that others can look to see whether or not those descriptions are legitimate. I spent a lot of time inside collections rooms when I was in the master's program and my PhD visiting museums all around the country and several other places in other countries. And every once in a while I come to a specimen and say, okay, you thought this was a Mosasaurus. And it's not a Mosasaurus tooth, it's actually this other thing, but that's because the person who did the original description didn't realize that they should have said Mosasauridae, just like it's a mosasaur. They accidentally went too far and says it's a Mosasaurus, which is a particular mosasaur amongst the group. So, there are cleanups that can happen there, but that wasn't even published data, that was just So in looking at these big data sets, I would say that unless you have good reason to think that your data are incorrectly coded, you should be able to trust them. And if you think that the data are incorrectly coded, it's actually incumbent upon you to show why that's the case. And so I've worried sometimes when creationists say, oh, that's evolutionist data. Well, every bit of data that we are all taught by evolutionists, not all. I mean, Dr. Humphreys was talking about the rate team. You guys went and collected your own data.
Well, we had an evolutionist actually make the measurements.
Well, then I don't trust what you did.
Okay.
No, right. And so some others in theology especially refer to this as that we have common grace, that we have all been bestowed with God with his image. And as a result, we should be able to understand certain things about the world. It might take a lot of training to get there, but whether I see a bone this way or that way shouldn't really depend on whether I'm an evolutionist or creationist. It's an anatomical question, not a historical one.
Something to follow along with that, and in creation, I think we talk a lot about the need to separate data from interpretation, right? And I think this is clearly a case of that. And one thing that struck me listening to your presentation yesterday is that I think it was the mosasaurs where you showed multiple trees that were generated from the same data through different, with slightly different parameters in how they built these family trees.
Yeah.
And I think it's probably significant that if they were, let's say, faking the data to match an evolutionary tree, they weren't doing a good job at it,
Right.
since they got very different trees as they ran through these different processes. And so it suggests that the data is real and that the evolutionary tree is one way to put that data together, but a creationist and someone doing baraminology in particular could analyze the exact same data, the same spreadsheets, and come up with what we would argue is a better explanation for how these organisms are divided, as opposed to assuming that they're all related.
I think that's a really good observation. Yeah, that paper on the mosasaurs by Simoes et al. Is really just a wonderful read in scientific humility, because they talk about the different types of parameters that they use for this data set, how they've worked to clean up previous data sets on mosasaurs. I mean, the first cladistic mosasaur data set was published by one of my former professors, the person who got me interested in mosasaurs, Dr. Gordon Bell. And his data set was the standard for about 10 years. But it was eventually usurped, or improved upon by some of his friends and colleagues and other people who built a better one as more and more specimens came on and more careful work was done. But the way that they describe how they go about and the analysis that they did and how they have these different approaches to building evolutionary trees, and then at the end saying, and we can't adjudicate which of these methods is actually the best, because they're each based on certain kind of a feel for maybe how it should be done, or this does a better job at doing this, that, or the other thing. But in the end, they said, but we can't tell which one it is. And so while we've got a good understanding of certain mosasaurs being connected with other ones, this big block here and this other block here, we're still not really sure how the blocks themselves get related, because these programs do it in different ways. And unless we knew exactly how evolution worked, but that's what we're trying to find out, right? So they're stuck in this kind of chicken and egg thing, but they're honest enough to talk about it. And not honest enough to talk about it in a way where now I have some gotcha quote. Oh, I can show you what the evolutionists really think. That's not it at all. It's rather, no, this is scientists being honest about things. And the last thing that I want to do is give that illustration and then make you think, oh, well, the evolutionists don't know what they're doing. No, they really do know what they're doing. In fact, they're very self-conscious. The good ones are very self-conscious about what the data can and can't tell them and what their analysis can and can't say about things.
One final thought on that is that when you talk about created kinds and the creationist alternative in trying to organize this biological data, is that we do have a little more guidance into where we're trying to go. We expect to find distinct created kinds. Whereas with the evolutionary counterpart, you're building an evolutionary tree, there's no way to know which tree is better than any other tree. So at least in the creationist version, we have some idea of what a robust created kind definition would look like. We should see that there's real discontinuity. It's a different kind of animal from other kinds of animals, and they are more similar to each other. And we can say, this looks right. We can probably be happy with this.
Yeah.
You don't have that same level of confidence, it seems, on the evolutionary side.
Yeah, sooner or later, everything's got to be related to everything else. And for the evolutionists, there is no biological taxonomy that is real except the species. Every other unit, the family, the genus, et cetera, are all artificial. And I have to agree with them in part, except for there is a kind. So, we have species, we have populations, we have individuals, but a genus is a collection of species that we think are actually pretty closely related to one another. And then a family is a collection of genera, multiple genus, that are probably connected to one another. So for us as creationists, we can recognize both the Linnaean taxonomy that we're used to. We can also recognize some of the evolutionary taxonomy that's used. But we can accept the reality of species, but we also know that there's a higher reality. There's something fundamental to the creation in which we have these kinds. And that should hopefully point us in a better direction.
Excellent. Okay, a question for Ron Payne. So you had to skip over some things at the end because lunch was waiting. But I wish we had the picture because it'd be nice to show everyone, but I saw briefly you had that photograph from Burlingame Canyon and those repeated alternating layers of sediment in the Walla Walla Valley. And these are believed to be deposited from or by the Lake Missoula flood or floods. And it's one of those important sites for that whole discussion. And you mentioned, I saw on the slide, that there's a Mount St. Helens ash connection to that story. So would you briefly summarize what's in that canyon and why it's significant to the question of how many Lake Missoula floods we're talking about?
That's a good observation. There was in the Walla Walla Canyon, like I was starting to share briefly, that was a artifact of what is thought to be repeated surges of water that went up from the lake that formed behind Wallula Gap downstream from Pasco that collected all the water coming down through the scabland areas, but didn't have enough time to simultaneously go through that gap down the Columbia River Gorge. So there was a surges of water that accumulated this lake around the Tri-Cities. And that lake got big enough where surges of water went up the Walla Walla Canyon to the east, and to the west went up to the Yakima Canyon. You had similar layers forming in the Yakima Canyon too. So the Walla Walla Canyon called Burlingame was actually an accidental canyon that was formed when an irrigation ditch was purposely diverted because of a potential flood that they were hoping would not damage the fields. Well, it ended up cutting this big canyon in a field and exposed this layering system called the Burlingame Canyon. And it had, roughly 40-some layers that were exposed and maybe more below. And it's believed that was a artifact from surges of water that went up and down, back and forth as that lake around Pasco rose and was reduced in volume because water was coming from every direction north of there. And so one belief is that those layers were deposited by surges that were low speed and deposited those layers. The other alternative was that they're represented individual floods, that one layer represented an actual entire Missoula flood. The interesting thing that happened is that in between down about, somewhere in the mid-range of that, there was a small layer of white ash that was recorded or is there. And so that was initially more evidence that it was individual Missoula floods that were depositing these layers, and then during one dry period we had a volcanic eruption from Mount St. Helens that deposited this ash layer. And then you had another Missoula flood event, which continued the layering. So that's an argument for multiple floods because it made kind of sense. But there's another way to look at it, is to what caused that ash layer. And one of the proposals that Michael Ord, for example, has proposed is that because of the volume of water that was going down the Columbia River, like you were talking about today, when you have some type of weight effect on the surface, it will sometimes cause stress that results in earthquakes in other areas. And so that was what he was proposing, was a cause of that layer during a single flood event where it sort of stimulated Mount St. Helens to erupt during the flood event. And that ash settled during one of those surges in between one of those layers. So there's multiple ways to look at it. It basically is evidence that you could use to demonstrate either viewpoint about multiple major floods versus one major flood with an eruptive event in the process of the flood. Does that make sense? I don't think there's really any way to tell on that evidence alone, either way, to make a decision about that. You have to bring in other factors to determine whether there's evidence enough to support a single major flood or multiple major floods. And that really is independent of the ash layer. But it does cause a question you have to answer and think about. I don't know if that...
No, that's good. That's excellent, yeah.
That's where that layer thing comes in there. It causes an additional question that you have to have an alternative one way or another to determine whether the major, and we're talking about major flood.
Sure. Because the layers in Burlingame Canyon are almost identical.
They're all, well, actually, one of the rationales for a single major flood is that the layers tend to be thicker on the bottom than they are on the top, which makes sense for a major flood because the later surges would have less and less and less
Interesting, yeah.
volume of sediment it carries. So that's actually kind of leans toward the fewer flood event.
And this is a debate within the secular geology community as well.
A couple weeks ago, I was at Dry Falls, and I was listening to a presentation by a independent, a private concern that was kind of having like a big celebration there, and the ranger made an interesting comment out of the blue. He said, "Really, there's no real issue with how how it happened and what happened, and the sequence of what happened. But the real issue now is that the real controversy is how many floods happened, not what or how it happened." Does that make sense? And I thought to myself, that's exactly what the major issue is that we're dealing with in terms of questioning now, because there's really no question about the how and the what and what happened in what order, because we kind of know that, and everybody agrees with it. So there's other rationales for supporting a single major flood, or maybe one more at most, but a single one that with evidences in the Missoula area, in the Montana area, and also in the actual deposit area itself, which we could get into if we had time.
Excellent, thank you. Okay, to the other end of the table, Mr. Bill Hosch. Will we ever find coal in Spirit Lake? It's the question I got all the time at the center. Everyone always asks that. Is there coal in Spirit Lake?
No.
Checked.
No. The reason is you would need subsequent burial to get coal. And you probably would have had to have buried it by now, because you want to you want to pickle that stuff while it's still fresh, because otherwise those compounds will break down pretty quickly. And so, yeah, no indication of coal forming today. No one's even suggested that. But what the model does document is it helps to vindicate that you can imagine a scenario in a global flood where you can get coal forming in that manner. You can get a tree bark rich layer of peat on the surface of the continent. You can imagine it in that way. It doesn't prove that's the way your ancient coal beds formed at all, but it helps to vindicate that model. That's as far as it goes.
So it's a first step in the formation of coal.
Absolutely.
But
yeah.
we don't have any more geologic activity at a great scale anyways going on to take us any further down that cycle.
It would need to be buried.
Yep.
Yeah.
Good. All right, back to Dr. Humphreys. So this is in regards to your talk today on the rate project and helium leaking. And at one point in your talk, you compared the helium diffusion, so the leak rate, and the rate of decay of uranium, the classical radiometric decay rates. You compare them as two different hourglasses. Your argument is that one of those hourglasses, the rate has been sped up to a very high magnitude, right? That we've seen accelerated radiometric decay. So the question pertains to those two clocks. How do you know which one has changed? In other words, how do we know that we didn't slow down the rate of leaking helium to match the radiometric clock? How do you know which clock changed when you have that?
Well,
that
I can
distance?
only say what's more likely, and I touched on this a little in the talk. If you're going to slow down the helium clock, you have to mess with electromagnetic and chemical interactions, the interactions between atoms. And if God did that, then if he changed those things, he's also very likely to change the chemistry of life, living things, because things are very complex and tight and well set up. And if he changes the physical laws that deal with the atoms, he's apt to destroy life. So it's much simpler to simply change the physical law that deals with the tiny little nuclei deep within the atoms. That nuclear force is a short-range force, and changing that would not affect anything else. The chemistry of life, the size of the atoms, how the electrons interact with each other. One is a tiny screwdriver adjustment to the physical order of things, and the other is a sledgehammer. So I would think God would prefer a precision adjustment to just the nuclei rather than a sledgehammer adjustment to the atoms.
Are you against sledgehammers?
You're flanked by geologists right now who use them.
Tread carefully here, Dr.
And
Humphreys.
he's the one I described sledgehammering the granites. So.
Thank you. Okay, another question for Dr. Ross. And actually, for any of these questions, by the way, feel free to interact and interject with each other as well. This is a short question, but it's a big topic. Is the geologic column reliable?
Is the geologic column reliable? Yes. Yes, it is. It's often said that the only place you can find the geological column is in a textbook on geology. And that's not entirely true. My master's degree was in South Dakota. And in South Dakota, walking from the Black Hills out to the Badlands, I could step on virtually every single unit of geology with the exception of the Silurian. So Cambrian, Ordovician, Silurian's missing, but then on the way, all the way up into, basically today, and I could do that because the Black Hills are a group of granites that had been punched up through what were flat-lying sedimentary rocks, and so they all tilted this way. And so if you start in Mount Rushmore at the Harney Peak granite, you can eventually walk your way and find some Cambrian stuff, and you can find the great unconformity out there, especially on the north side towards Lead and Deadwood. But you can work your way through all the stuff. The further you get away, the higher up in the column you get. And so everything was there in the place that it would be predicted to be. The geological column was assembled in continental Europe and England, but then it was discovered to be applicable everywhere else we went. It's not that you're going to find the whole geological column everywhere. The way that you would get the whole geological column in one place is it has to be the low spot throughout all of the time in which everything is being deposited. So if it ever pops up, even for a little while, and gets sheared off, you end up missing things. If it drops back down, then you start accumulating again. So that's what happened with the Silurian, not only in South Dakota, but across much of the West. There's a big erosional scar right over there. So I can confirm with my own field work and observations that yes, it is. And it's true both on the macro scale as well as on the finer scale. If you start dividing out those units of geology, like the Mesozoic into the Triassic and the Jurassic and the Cretaceous, then you take just the upper Cretaceous and you start looking at that, yeah, it's a reliable feature that is empirically documentable. Because what you have is a hypothesis, the column, and then you have the data out in the world. You can check that hypothesis anywhere you go. And you will find that it works. You find a few places where things have been tipped upside down or something's been shoved over top, but you can trace those things out. Dr. Tim Clary at ICR did some really good work on the Hart Mountain Fault, where you've got Cambrian rocks over top of Cretaceous, and creationists in the past have used that as an example of the geological columns out of order. Well, it turns out there's a fault, and you can trace the Cambrian over top of the Cretaceous, but in other places it's over the Triassic, in other places it's over the Permian, until eventually you find where it's underneath the Ordovician where it ought to be, and it was a low-angle fault that just got shoved way, way over top, and that's been confirmed by boreholes and oil test wells and things like that. You can find that fault. So yes, it's part of the reality of the world out there, and any model of creation and the flood is going to have to adopt that as part of the evidence base.
I have something to add to that.
Yeah.
Go ahead.
You do too?
Yeah.
You want to go first?
Sure.
Go ahead.
Yeah, there's a reason why I don't like to question that there's some reality to the geologic column, and that is to give it up is to give up one of the best arguments we have for a global flood. There is a reality to the fact that the Cretaceous in Texas looks like the Cretaceous in Turkey. We have to appeal to a sufficient process to explain that, and the flood is it. Same thing with the Cambrian, same thing with the Carboniferous, same thing all around. We've got our best case for a global flood in the reality of the geologic column. To give that up is just foolishness. And the founders, like you said, in the history of geology, those are arbitrary terms. Somebody said, hey, we got rocks in England that look like rocks in Russia. Let's call it the Permian or whatever, and or the Cretaceous, and that's the way it developed. It was later on that the baggage got added, where they attached millions of years and all the evolutionary garbage on top of it. But as an arbitrary naming of the record, wow, what a useful tool! What a tremendous discovery that is.
What I was going to point out is that in the rate number 1 book, in my chapter of it, there's a figure that plots geologic date, or let's say the names of the fossil layers in the order that they're given, the whole geologic column horizontally, and then vertically the radiometric dates that have been recorded in the literature. There's a general correlation between the two. There's a lot of points scattered around this general curve, but they correlate. So the Cretaceous in Siberia probably gives on the average the same radiometric date as the Cretaceous in Texas. So that's additional evidence that it's reliable.
Excellent discussion. And I liked what you pointed out also, Bill, because I think the reason why this question often comes up is that a lot of us are first exposed to the geologic column as essentially a template for evolution. And so there's been, for a long time, that association that one means the other. But actually, as I understand the history, the geologic column predates evolution. You could, at least the baby steps in formulating it go back to even before the time of Darwin. So that really is a misunderstanding, I think, that occurs in the general culture as well, not even just among creationists.
Absolutely, yeah.
Yeah, just to jump in on that, when Darwin wrote and published The Origin of Species in 1859, the geological column was essentially established. There were only 2 units that have subsequently been added to the Phanerozoic record, the Ordovician and the Paleocene. So the Ordovician is above the Cambrian and below the Silurian. At the time of Darwin's writing, the Ordovician had not been recognized as something distinct, so you just went from Cambrian to Silurian. And you see in later editions of the Origin where he finally puts in the Ordovician. And it wouldn't be until geologists in North America discovered mammal fossil-bearing units above the Cretaceous that didn't look like the Eocene rocks in Europe and the Eocene stuff in North America. They discovered there was a unit in between there too. So again, this is an empirical reality where they're looking at rocks that are in vertical superposition or tilted superposition and saying, yeah, we can trace these things from one point to another, and we can follow the pattern of the fossils in them from one continent to another. And I think that's the big thing to understand, is that the geological record was built on initially. The radiometric dates came in later and confirmed the overall pattern to be correct. But the initial construction of the geological column was based on patterns of fossils that were found in stacked rock assemblages. And it's not just that I found this fossil here and that fossil there, and so I'll do that. But no, it was whole suites of fossils and then different ones above them. And so when you see multiple patterns in multiple places, it demands some type of unified explanation. I think Bill hit the nail on the head with that one, even if he did it with a sledgehammer.
Yeah, I'd like to challenge anybody who wants to question the reality of the geologic column. Read the book, get hold of that old book by Derek Ager called The Nature of the Stratigraphical Record. Here's a secular scientist who's calling attention to the very same things we're talking about, and he's saying, we have no answer for this as a secular geologist. It is a great read. Yeah.
All right, excellent. I think we are about at the end. We have one last question, probably an easy one, for Bill Hosch again. Is the Little Grand Canyon at Mount St. Helens, is it getting deeper or shallower since it was first eroded?
Is the Little Grand Canyon of the Toutle River, the drainage that was cut by the 1982 mud flow?
Is the Toutle River gradually, is it making that a deeper, steeper canyon over time?
Is it making it deeper and steeper? No, it's probably, it actually is down cutting.
Is it?
Yeah, so it's, the valley of the North Fork of the Toutle is making its way back to its probably original pattern, and that's why it's a big silt problem out there. It continues to erode quite a bit. It's rapid erosion going on, but I'm sure it's probably side cutting as well as down cutting today. I don't think it's dramatic down cutting like it was from the mud flow, and so yeah, it's probably side wearing as well as down cutting right now.
I think you can, last time I was on a hike on the hummocks, you can see part of you can see the riverbed, and it appears that there's some erosional characteristics below the original level of the 1982 cut.
Yeah, when you look at the that debris flow, the landslide debris, or the debris avalanche you call it, that rested in the valley there between Castle Lake and Coldwater Lake, man, you can imagine that infilling the whole valley, and it's down cut tremendously, and it wasn't all the 1982 mud flow that did it. It's done a lot of down cutting, but it's not the dramatic incision cut that was done rapidly.
Excellent. All right, we are about out of time. Last call, any questions here in the room before we close this up? Okay, Bruce, well, let me bring the microphone to you.
This is for Dr. Ross. I was wondering if you could comment on how you think the mountain ranges such as the Cascades and Rockies were formed according to your model.
Thank you. That's a good question. I'll preface that with I am not an expert on the Cascade Range by any stretch. I did take a couple of classes in Rocky Mountain geology when I was in South Dakota. That was a little more pertinent to our locale over there. So the Rockies are a fascinating mountain belt. As I mentioned in my talk, they aren't formed by collision like the Appalachians are. Instead, the Rocky Mountains are formed by a vertical motion, just like the Black Hills. They got punched upward. The most likely scenario seems to be that during the flood, but for my old age colleagues as well, they're looking at a similar process, just deeper in time. You had a plate that was coming underneath North America, was subducting and melting and producing a lot of volcanoes. So the volcanics that are in Idaho and Montana are part of the subduction and the melting, just like the Cascades, especially stuff like Mount St. Helens and Mount Hood, are volcanic mountains formed by the subduction of the Juan de Fuca plate today. So you just shift all that stuff over. You don't have Washington yet. As the Fowleron plate is going down and under, it is kind of suctioning North America downward like this. And that is allowing a huge area of North America to be inundated. And this gives us things like the Niobrara chalk and the Pure Shale, the marine units that are inside the interior of the United States. But at some point, the Fowleron plate actually fractures and breaks, and part of it, say around my knuckles here, breaks off and starts traveling down into the mantle on its own. That releases the suction, and there is a rebound that pops vertical and pushes a bunch of granite upward. And that's when you have the beginning of the Laramide orogeny that starts the Rocky Mountains and the Black Hills. So if you go to Denver or you go to the Black Hills or something like that, you're driving, and then all of a sudden it's just like the mountains are just here. There's no foothills. You're just driving flat through Kansas and through Colorado forever. Forever. I remember I flew into Kansas City on the other side of your state, and I drove out into Kansas and I passed Lawrence, and then after I passed Lawrence, there was a sign that said, 25 miles to this town, 30 miles to this other town, Denver, 678 miles. There's nothing else to really talk about. But when you get to Denver, all of a sudden, there's just, it's called the Front Range, because right up front, you just have this vertical motion. So that is the mechanism. That was something that was missing from Wegener and continental drift. He had no idea of a vertical tectonic like that that happened, but it happened likely because of a breaking of a subducting plate that caused buoyancy rebound. And as for the Cascades, they're formed by the subduction causing melting. So as the slab goes down, it gets hot in the mantle, part of it begins to melt, and the molten material comes up through and starts creating volcanoes. So all the volcanoes that pockmark the area here have their source in sediments and partial ocean crust that is right now, 60, 80 kilometers deep, and is melted and is traveling its way through fractures in the crust until it can get all the way up to the top, or it gets stuck, and you end up with granites and similar types of rocks there. That's as good as I got.
Yeah, the Cascades, I think, are, when you shave off the modern day Cascade peaks like Mount St. Helens, Mount Rainier, and so on, you've got this kind of irregular plateau. And what is it? it's utterly catastrophic volcanic material. This place was, you're right on the leading edge of extreme violence of anywhere in the world. We're right on the Pacific margin here. And so that's the Cascades. And to return to the Rockies, so it's fun to read the literature on how the debate has raged down through the decades about how the Front Range was uplifted. And it's really interesting because people want you see how people are trying to press the everything explained by lateral movement of plates, and they try to make the Front Range fault zones to be vertical, but they shallow with depth and become like a sled runner out further to the west, and with very little evidence. And it's really funny to see because it really looks like they just popped right up. And but the Rockies are pretty diverse too. That's just one part of the Rockies, yeah. Good.
Excellent. Okay, I think that's all for our time now. So please join me in thanking our speakers. And that is the end of our program. So thank you all for your attendance. Thank you to everybody online. You probably can't see me because I've wandered off the view of the camera. And just hope you have a blessed evening and that this weekend has been an encouragement. So thank you again.
Thank you, Zach.
Thank you.
Thank you.